Hey there, chemists. In this lesson, we're going to look at acid derivatives, which are derivatives of carboxylic acids. So instead of an OH, we have some other group here. X normally implies a halogen, but it could be a variety of things, as you see in the little chart that's down below. The main thing to look at with these reactions is they do substitution reactions. Overall, these are substitutions. Substitution. And we can convert whatever this X is into something else. Normally we look at addition reactions, where something nucleophilic attacks the carbonyl, the electrons go up, and then you stop. We'll see in this case that bond will actually reform and then separately kick that X group out. In fact, let's just draw that off to the side. That's why I left this space here. If we have some generic carboxylic acid derivative, and we react it with something that can act as a nucleophile. The nucleophile can attack the carbonyl. The pi bond still goes up to the oxygen. You get an intermediate. It's a tetrahedral intermediate. And then in a second step, the main part of this mechanism is that you reform the carbonyl and then that X group leaves, whatever it is. We've actually seen a couple of examples of this type of chemistry, but we're going to really focus on it here. In fact, this is called acyl nucleophilic substitution because it's so common. The acyl group is just whatever is attached to the X group, the carbonyl, without defining it as an acid or an acid chloride or anything like that. So in the middle of your notes here is a chart with some of the most common acid derivatives, just a functional group review to start. See if you can guess as we go along. The first one is an acid chloride. You have these on that functional group dictionary from Orgo 1. Right next to it is an anhydride. It's called that because you get that from two carboxylic acids coming together and losing a water molecule. So anhydride analogous to anhydrous, losing water. Then we get to an ester. And the one we've been working with a lot after that, a carboxylic acid. Then one we've seen a little bit as well in the ketones unit, the nitrile. And lastly, one we haven't seen too much of at all, the amide. So they're listed in this way to show two things. Number one, the fact that the most reactive one is all the way at the top. For the most part, acid chlorides are more reactive than any of these other derivatives. And among the more stable derivatives is all the way at the end, the amide. This is typically the least reactive. Amides make up this special bond between the nitrogen and the carbonyl. That's also called a peptide bond. So you and me are made of many things, including peptides. So it's good that they're quite robust. The second thing that this chart is meant to show is how these can all interconvert between each other. They're all very related. And obviously, if you start with the most reactive one, you could convert it into pretty much any of the others. And that is also true that we could take many of these and turn them into other acid derivatives as well. I'm going to annotate your notes just a little bit more and remind you of one reaction we learned recently, which is thionyl chloride, SOCl2. That's thionyl chloride. And that will convert an acid chloride into an acid. And that's really useful. It's also worth mentioning any of these groups, any of them can be converted. Oh, excuse me, I misspoke. It'll convert an acid into an acid chloride. Thionyl chloride works in this direction. If you can get to the acid, you will go to the acid chloride. How do you get to the carboxylic acid from anything? That's hydrolysis. Hydrolysis of any carboxylic acid derivative, so I'll abbreviate it here, will get you to the carboxylic acid. Hydrolysis, for our purposes, typically just means aqueous acid. So any derivative goes to the acid. Okay. Now the rest of this for today, we're just going to look at some reactions, specifically reagents that we can use to interconvert different functional groups. I'm not going to go through each derivative on a separate day. They're so similar, we can summarize them all in one lesson today. We'll start with the most reactive ones, the acid chloride, and many of these are reactions we haven't seen before, but using a little bit of common sense, you can figure out what reagents must be missing. Even if I posed this first one to a 10th grade chemist, as long as they knew how to read line structures and said, can you balance this first reaction for me? Yeah, it's just water. Now I know I just said hydrolysis, H3O plus, will do this transformation, and yes, that's also true. But it's the net addition of water that reacts with acid chlorides. In fact, we've seen this chemistry before. Acid chlorides are very reactive, and they hydrolyze with water to make the carboxylic acid. Right below it, we have one that's pretty similar, but we make an ester instead of the acid. The first one, we made the acid. The second one, we're making an ester. So instead of water, what do you think we're going to use? We're going to use an alcohol, specifically methanol. Depending on what alcohol we use, that will dictate what ester we get. Next, we've got an amide. And again, if I just balance, what am I adding to make this amide with a byproduct of HCl? It's going to be an amine, in this case, methylamine. Okay, so I want you to hit pause and try to do the other 5 that are in front of you, all reactions of carboxylic acid chlorides. Some of them new that you have to decipher. Some of them are actually old from Orgo 1 or earlier this semester. But hit pause and see what you come up with. Okay, so if I do the next one, here we're making an anhydride. This was meant to be similar to the first 3, and that you sort of just figure out what group gets added. We are adding this group and an H. So I put those together. That means we're adding a carboxylic acid. In this case, it's just acetic acid or ethanoic acid. But any carboxylic acid would react with an acid chloride to give you the anhydride. Next, we get to some old chemistry. We're making a tertiary alcohol in this one. And for this, I got to go back to Orgo 1. This involves an organometallic, which adds twice to the acid chloride. So I need 2 equivalents of an organometallic. This one is methyl Grignard, MEMGBr, and then followed by an acidic workup. In fact, it's the same reagent for the next one, except we're not going to use a Grignard, we're going to use a cuprate. Because remember, cuprates do not react with ketones. So we can stop at the ketone for the third one. Remember how you write a cuprate? It's 2 of the R group, in this case a methyl, followed by copper and lithium. That's just how you write the reagent. Okay, and then how do we turn it into a primary alcohol? For that, we're going to use lithium aluminum hydride, or LAH, also with an acidic workup. There's a reagent we're going to see quite a bit in this unit, which is diisobutyl aluminum hydride. This stops at the aldehyde. You can kind of remember that most acid derivatives with dibal will make an aldehyde. The reagent is also a source of hydride. It looks like an aluminum with a hydrogen. So there's your hydride, a hydrogen attached to a metal. It's usually negatively charged as a hydride source. And it's got 2 what are called isobutyl groups attached to it. So you get isobutyl, aluminum hydride. And then lastly, to turn an acid chloride into a ketone, if you just used the cuprate, like we did right next to it, that's so okay. I might write phenyl cuprate, that's fine. Or I'm going to say specifically, since this is a ketone that's off of a benzene ring, you could use a Friedel-Crafts acylation here. So this is a little more specific, but just to remind you, it's also a reaction of acid chlorides. It's actually the most common time we've seen acid chlorides lately is in the Friedel-Crafts reaction. Okay, I want you to hit pause once more and see if you can figure out the reactions of the esters and the anhydrides, which are down below. Some of them interpret, and they'll have a lot of similarities to up above, and then some might be throwbacks to old chemistry. Okay, if you've unpaused it now, or if you're just skipping over that pause button and eager to get to the answers, here we go. The first one is hydrolysis with water, or H3O+. The second one is an alcohol, specifically methanol for this example. And the third one is methylamine, so it's an exact mirror of what we have up above. It's just a repeat of what we have up above. In fact, right next to it is also more of this. Now we're into ester territory. That's all I have for anhydrides. They actually do a lot of chemistry that's really similar to acid chlorides, so I didn't bother putting all of them up there. Ester, we can use a hydrolysis. Esters are slightly less reactive, so we need hydrolysis to do this. Just water will react with an anhydride or an acid chloride, but we need something a little more reactive to get an ester to go to the acid. Methanol, under acidic conditions, will get you to a different ester. This is ester to ester, but we're changing one ester into another ester. This is called a trans-esterification because we are literally just swapping out one ester for another. And then the last one in this column is a carboxylic acid. That will shake your ester and turn it into a carboxylate. Okay, so a few more with esters. This is also meant to mimic what's up above. To take an ester and turn it into a primary alcohol, you can also use LAH. Once again, diabal will change the derivative, the ester, into an aldehyde, so same as above. And at the bottom, we've got an ester turning into a tertiary alcohol. Here we want two methyls to attach, so methyl grignard. Or methyl lithiate. It's easier to write methyl lithium, it's fewer characters, so I'll write that this time. Just to remind you, lithiates and grignards are almost interchangeable, aren't they? Okay, so I actually flip to the back, and we're going to do a few more. We're going to look at amides and nitriles just to fill in the notes that you have and act as a refresher of some reactions that you've seen. Most of these we've seen in our other units, specifically reactions to make acids, and then recently reactions to make amines, but they started with these things, so we're intercepting different functional groups. They started with amides. Once again, hydrolysis of an amide will get you to the acid. If you want to make an amine, this is a amide starting material. Lithium aluminum hydride will do this. That's a very involved mechanism. If you want to go look up how that works, it's pretty lengthy. But it's interesting if you look at the overall transformation. It reminds me of the Wolff-Kishner because the carbonyl completely goes away. But the Wolff-Kishner is for ketones and aldehydes. Here we are in amides. They do different chemistry. The one after that is the Hofmann rearrangement. That's bromine and KOH. We saw this in our amines unit. Hofmann rearrangement. And notice you get an amine with one less carbon, one less C. So we actually pluck out this carbon and it gets lost as a CO2 molecule. So at first, these are really similar reactions. They both take amides and turn them into amines, but the second one, the Hoffman, loses that carbon. Just keep that in mind. And then the last one, here's a new one. This lets you make a nitrile, which happens to be the last group we're going to talk about today. One way to make a nitrile is from an amide, and it does a dehydration with POCl3. Dehydration means you lose water. And this one actually isn't as hard to remember. If you think about the tautomer of an amide, this is the less significant tautomer. Remember, tautomerization is how you go from something that looks like an enol to a keto, but here we have this tautomer of an amide to the main form of the amide. POCl3, you should remember, loses H and OH to make an alkene. Here we're losing H and OH from this less abundant tautomer of the amide, and you get an extra pi bond between the two carbons. That's actually sort of how it works as well. We're not going to do the mechanism for that, but that's how you get that nitrile. To the right of that, just to finish up for today, reactions of nitriles. Nitriles can undergo hydrolysis to make a carboxylic acid. We actually did that mechanism earlier in this unit. Nitriles can also react with Grignards to make a ketone. And now that you've seen it a couple of times, how might we make an aldehyde from an acid derivative? We're going to use dibal, diisobutyl aluminum hydride. And then one last one that we have seen, to take a carbon-nitrogen triple bond and make it a carbon-nitrogen single bond, you hydrogenate it. H2 and palladium. So there's a whole bunch of reactions, some of them new, some of them old, that we can add to our repertoire for how we can make acid derivatives and react acid derivatives all in one shot. There's a couple of homework problems I want you to try and submit to show us how we could fill in these syntheses. And then moving forward, we're going to focus just on some mechanisms and reactions that apply to these derivatives, and that'll take the next several lessons, but we'll get to that one day at a time. Okay, so that's how we deal with acid derivatives.